Thanks for the introduction. Good morning. I'm very glad to be here to give this talk. Today, my talk is a danger of using fully homomorphic encryption. A look at Microsoft SEAL. First, let me introduce myself. My name is Zhiniang Peng. I got my PhD degree in cryptography from South China University of Technology. Now I'm a security researcher at Qihu 316. And my Twitter account is Edward Peng. You can reach me on Twitter if you have any question on this topic. For now, my research area focuses on software security, applied cryptography, and street hunting. About this talk, in this talk, I will first give an introduction to fully homomorphic encryption, and then I will to tell you what is homomorphic encryption and why we need homomorphic encryption and the application of homomorphic encryption. Then I will introduce the most widely used homomorphic encryption library, SEAL, which is open sourced by Microsoft. Many companies are now currently using SEAL to build data security application. It seems that the fully homomorphic encryption is very close to practical. However, our research found out that there are many security pitfalls and security risks when you're using fully homomorphic encryption. In this talk, I will take SEAL as an example to introduce the security pitfall and the security risk in fully homomorphic encryption. And we will also give some demo about it. This topic may be very hard to understand for non-cryptographer, but I will try to make it as simple as possible. Before get into the topic, let's see some news here. As you can see in the picture, people are now worrying about their personal privacy being recorded by some big internet company. For example, the app the app know you where was last night, and they are not keeping it secretly. Google is recording you through a mobile phone and monitoring millions of conversation. So data leakage nowadays become more and more serious. Almost every month we can hear some news about data leakage, and data security and the user's privacy now become a public concern. So many people might think that why not encrypt our data before give it out to the cloud? But this will make the cloud cannot provide us a service based on those data. It will be nice to be able to encrypt our data before send it to the cloud, while still allowing the cloud to do some search, sort, addition on those data on my behavior. It will be very nice to be able to encrypt my query to the cloud while still allowing the cloud to process them. Then the cloud can return an encrypted answer to me. Then I can decrypt this answer and get a result. The picture in here shows our dreams, but how can we achieve these dreams? So here comes fully homomorphic encryption. Before talk about fully homomorphic encryption, we first talk about encryption support homomorphic addition. In this picture, as you can see, we have an encryption algorithm which supports homomorphic addition. We have two ciphertexts here, A and B. If we want to get an encryption of A plus B, we should first compute A plus B and then encrypt the result of the addition for normal encryption algorithm. But if we have homomorphic encryption support for homomorphic addition, then we can do it like this. We can first encrypt A and B. Then we can get the encryption of A, EA, and encryption of B, EB. With homomorphic addition, we can compute EA plus EB to get EA plus B, which means that we can do addition computation on ciphertext. By the way, the original RSA encryption, which was very famous, is support the homomorphic addition. Besides homomorphic addition, here is another property, the homomorphic multiplication. Just like the last slide, we can see that in this picture, homomorphic multiplication means that you can do multiplication computation on the ciphertext. The pure AGMA public key encryption algorithm support homomorphic multiplication. So here comes a fully homomorphic encryption, as shown in the picture. For any ciphertext x1, x2, and xn, we can encrypt them as ex1, ex2, and exn. Then we can do arbitrary computation on those ciphertexts to compute any target function f. F can be a machine learning algorithm, or simply to do some search on the ciphertext. The concept of the fully homomorphic encryption has proposed many decades before, but not until 2009. Gintris proposed the first fully homomorphic encryption algorithm. So what can we do with fully homomorphic encryption? We can use it to protect your data while still allowing others to provide some service on it. Here is a famous metaphor about it. Suppose you are a boss of a jewelry factory. You hire some worker to do something on your jewelry. But the worker cannot be trusted. They may steal your jewelry while doing his work. So how can you protect this kind of things to happen? You can put your gold in a locked box, and then you can keep your key. Let the worker work on it with a glove box. Then after the work is done, you can unlock the box and get the jewelry. This is just like how fully homomorphic encryption saves your data from malicious servers. There are many applications of homomorphic encryption. For example, you can outsource your computation to the cloud without leaking your data, or you can do some machine learning on some encrypted data, or the cloud can do some other service without knowing the client's privacy. We can divide the application of FHE, homomorphic encryption, into two categories. The first category is that the data is private, but the function to be computed can be public. Another category is that the data is private, and the function to be computed also should be kept secret. The difference of those two categories is that whether the function to be computed is need to be kept secret. For application with private data and a public function, the model is shown in the picture, as you can see. The client sends his data to the cloud. Then the cloud do some computation on it. Of course, the data is encrypted. But there is no need to protect the function the cloud computed from the client. An example is that here we can use fully homomorphic encryption to do disaster prediction. The client sends their encrypted generic data, health data, lab result to the cloud. And the doctor sends the function to be computed to the cloud. Then the cloud can evaluate those functions on those encrypted data and return the encrypted result to the patient, and the patient can get the results. For application with private data and private function, the model is shown in this picture. The key difference from the former one is that the model to be computed is also an IP of the cloud. For example, the cloud company may spend a lot of money in training a good machine learning model. So he definitely do not want to give this model to other ones. So in these scenarios, both data and the function to be computed should be kept secret. To achieve this, we need the homomorphic encryption to have circle privacy. It's an additional requirements in many fully homomorphic application. The invariated ciphertext should hide the function f. Okay, That's all for the introduction for the fully homomorphic encryption. Here we come to the Microsoft fully homomorphic encryption lab, the SEAL. It's an implementation of fully homomorphic encryption. Here is a quick background of the SEAL. SEAL is a homomorphic encryption library from Microsoft Research. The first version was released in 2015. On December last year, Microsoft officially open sourced SEAL on GitHub. SEAL is developed in standard C++, and it can be used in many devices. It implemented two famous homomorphic encryption algorithms, the BFV algorithm and the CKKS algorithm. In this talk, I will only focus on the BFV algorithm, but the same problem also happens in CKKS. SEAL is a simple and easy to use library. It comes with detailed example in this project. You can play with it after this talk. Some people are saying that the homomorphic encryption is too slow to be used in real application. In my opinion, the performance of homomorphic encryption has improved a lot in recent years. Microsoft used SEAL to build an encrypted handwriting digital picture recognition program, the Kryptonite. It can make 16,000 prediction per hour with 99% correct rate. This means that you can process 16 encrypted picture per second in a normal computer. That was the result in 2016. Today, this can be done probably 100 and 1,000 times faster by using GPU or FPGA. In our experiment, we can do logistic regression prediction on 10,000 of encrypted data in just 5 minutes. It's about 300 times slower than directly using scanning on those plaintext. Summing 100 million random float between 0 and 100, you need less than 900 milliseconds. And those message and the message expansion is about 8. So as we can see, I show in these slides, the performance of SEAL seems reasonable. Okay, so how does fully homomorphic encryption actually works? Here I will give a brief introduction to how it works. First, I will introduce a ring LWE problem to you. Every public key crypto system is based on some hard problem. For example, the RSA is based on integer factor problem. Nowadays, almost all the practical fully homomorphic encryption scheme is based on the ring LWE problem. In the ring LWE problem, we have a polynomial ring R. All the elements in these slides are some elements in the polynomial ring. However, to make it simple to understand, you can just think all the elements here are just some integers, so you can easily understand them. So here is a simplified version of the ring LWE problem. There was a challenger, then the challenger gave you some A1, B1, A2, B2, and AK, BK, with BK equals AK times S plus some small number EK. Then we call AK, BK the ring LWE pairs. Your mission is to find S, where S is a random number, and the EI is very small in here. Of course, if EI equal to 0, then you can simply find S by use Gauss elimination. However, EA here is some unknown small integer, so it's not easy to find S. If you can find S, you can solve ring LWE problems. Here is another version of ring LWE problem. It's a decision version of ring LWE problem. It works like this. Also, there will be a challenger and you. The challenger will give you A1, B1, A2, B2, and IK, BK. Your mission is to tell the challenger that does there exist S and some small integer E to make those AI, BI become a ring LWE pair to satisfy this equation. All those AI, BI are just some random numbers. Both the ring LWE problem and the decision ring LWE problem is a hard problem in mathematics. So even Gauss cannot solve those problems. If we can build some crypto system based on those problems, we can make sure our crypto system is secure. If an attacker can break this, the crypto system, means that an attacker can solve the ring LWE or the decision ring LWE problem. Then we can suppose that he is smarter than Gauss, because we know that no one can smarter than Gauss, so no one can break the crypto system. So how can we build a fully homomorphic encryption based on ring LWE problem? Here is how the BFV algorithm works. In the secret key generation, we simply choose some secret key S to generate a public key. Here S is a polynomial in the polynomial ring R, but to make it simple, you can think S is small integer. To generate a public key, we can just choose a random a random number A and a small error E, then publish a public key pk0 equal to minus A times S plus E, and pk1 equals A. Here we can see that pk1 and pk0 is actually a ring LWE pairs, so nobody can recover S. Otherwise, he can solve the ring LWE problems. To encrypt a message M, we choose a random number U and a small error E1 and E2. Then we can compute the ciphertext C0 and C1 using the public key like this. Here I will not go to a detail, but the result is that C0 and C1 become a decision ring LWE pairs. Because attacker cannot solve the decision ring LWE problem, which means that in the view of the attacker, C0 and C1 is just like some random values. And the message is encrypted with some random pad, so he cannot recover a message. In the bottom, we can also see that the ciphertext is consists of C0 and C1. So we can consider the ciphertext is a polynomial fx equal to C0 plus C1 times x. Then how can we decrypt this ciphertext? For ciphertext fx equal to C0 plus C1 times x, we can just substitute the variable x with the secret key s. Then we can get the then we can get this equation. After some simple math, we can think that fx equal to v plus in the bottom you can see fx equal to v plus delta times m, where delta is a public parameter and v is much smaller than delta, so we can recover the message m. If you have two ciphertexts f1 and f2, to do homomorphic addition on those ciphertexts, you just add those polynomials together. You get f3x equal to f1x plus f2x. Then we have f1s equal to, because we have f1s equal to a small number v1 plus delta times m1, and f2s equal to small number v2 plus delta times m2, then we can know that the f3s is equal to v1 plus v2 plus delta times m1 plus m2, which means that f3x is equal to a small number in the bottom. You can see that small number V3 plus delta times M1 plus M2. So we can see that the BFA algorithm supports homomorphic addition because you add some ciphertext and you can get the addition of the plaintext. If we have ciphertext F1x and F2x, to do homomorphic multiplication of those ciphertexts, you just compute F3x equal to F1x times F2x. Because we have F1x equal to small number v1 plus delta times M1, and F2x equal to small number v2 plus delta times M2. So we can get that the F3x divide delta equals v3 plus delta times M1 times M2. So we can see that the BFA algorithm supports homomorphic multiplication. Remember, this is an oversimplified version of BFA to make you understand easily. The real lattice-based cryptography is much harder than this. So here we introduce the BFA scheme and the homomorphic property of BFA encryption. However, this is, the original BFA algorithm is much more complicated than this. But this introduction is enough to make you understand the problem behind homomorphic encryption. If you want more detail of BFA encryption, you can read the original paper in here. By the way, you can play with BFA algorithm by using my implementation. I have read a version of the simplified BFA. You can find the source code in my GitHub. From the above slides, we can see that the BFA algorithm encrypts message M to a polynomial fx. The decryption is very simple, just to substitute x with the secret key s. Then we can easily recover the message M. We can consider that the message is actually blind by the ring LWE pairs. So we have the probable security for BFA algorithm. If an attacker can do choosing ciphertext attack to distinguish ciphertext, then he can also break the decision ring LWE problem. This will happen with extremely low probability. So we can conclude that the BFA algorithm is IND-CPA secure. However, in encryption system, choosing plaintext attack is not the most powerful attack model. In many scenarios, attacker can launch a choosing ciphertext attack, which means that attack is given to access to a decryption oracle. He can ask the oracle to decrypt some ciphertext for him. The BFA algorithm does not meet the IND-CCA security, which means that it's not secure when the attacker can do some choosing ciphertext attack. Actually, all the fully homomorphic encryption scheme cannot guarantee IND-CCA security. There is some theoretical research on CCA secure fully homomorphic encryption. However, the performance is unacceptable. So we can conclude that all the fully homomorphic encryption cannot guarantee security in IND-CCA scenario. But do we really need IND-CCA security? The answer is yes. Yes, we do, because in real scenario, attacker can always have opportunity to ask for decryption. IND-CCA security is now a standard requirement for encryption scheme. Besides, scenarios that require homomorphic encryption often require IND-CCA more than other scenarios. This is because there always a rich data flow between data owner and the cloud. Or you always have some multi-part cooperation and data exchange in these scenarios. If the decrypted data is leaked to others, then it will break the CPA models. It will break the system. Here I will present a one query attack. Suppose the attacker can query the decryption oracle for 1 time. This is realistic in many scenarios. Then the attacker can create a malicious ciphertext with C0 equal to 0 and C1 equal to delta, as you can see here. Then he can give this malicious ciphertext to the data owner. The data owner decrypts this ciphertext by substituting X with S. Then the decrypted message is equal to private key S. So the attacker, if the attacker can get the decrypted message, then he can recover a secret key by just ask a decryption oracle once. This is extremely dangerous. Not only SEALs, every homomorphic encryption faces the same problem. Here is a small demo I make of the one query attack. In this picture, we define the function recover key. This is simply a simple function used to recover a secret key of BFV by just ask the decryption oracle once. Here we first generate a secret key and public key for BFV scheme. Then we call the recover key function. For the default parameter of cell, in less than just 1 millisecond, the recover key function will print out the secret key of BFV algorithm. So it's a very simple and dangerous attack. The source code of this attack is published in my GitHub. You can check it by yourself. So the countermeasure to this problem is that just do not use fully homomorphic encryption in any scenario that the decrypted result might leak to the evaluator. Otherwise, there is no encryption at all. But in a real scenario, the decrypted result may leak to some other people with or without our notice. So how can we make sure there is no leakage at all? This is a very critical problem for using homomorphic encryption. 2 months ago, I have visited Microsoft research to collaborate with Microsoft SEAL team to work on this problem. We are going to build a new type of mitigation for those issues. It should be available shortly in SEALs. So here is the second problem. Here I will first introduce a new application of fully homomorphic encryption to you. The private state intersection, the PSI protocol. In a PSI protocol, we have a sender and a receiver. The sender has some collection X, and the receiver have a collection Y. The PSI protocol is going to compute the intersection of X and Y and give the result to the receiver. In the meantime, everything else is kept secret. The sender shouldn't know anything about Y, and the receiver shouldn't know anything about X, except the intersection. So the PSI protocol is useful in many scenarios. For example, it can be used to build a private contact discovery in end-to-end encryption, IM such as Signal, WhatsApps. The user have some contract in his phone, and he want to know which of his friends are also using Signal or WhatsApp. So he can do PSA with the Signal server. He can get those friend lists without leaking his contact list to the server. How to achieve this? In CCA 2017, Chen proposed a PSA protocol based on homomorphic encryption. The idea is very simple. The mobile user just encrypt their contact list X using homomorphic encryption and send the result send the encrypted X to the server. And the server can do some homomorphic computation with his local database Y and get the encrypted result of the intersection of X and Y. Then the server sends the encrypted result back to the client. The client gets the result, and he decrypts it, and he can get the intersection of his contract links with the server. The protocol seems to work well, but actually it's vulnerable to two attacks. The first attack is that the CCA attack on these scenarios. Suppose you are the client and you get a list of your friends who are using Signal or the apps, and the next thing you do is probably add them as a friend in Signal and in the apps. Then you will send the intersection of X and Y in plain text to the server. This is actually information leakage to the server, because the server can get the decrypted result. So the server can make a malicious ciphertext and launch a CCA attack against the client. And then he can recover the private key of the client and decrypt everything. From this example, we can see that there are always many unexpected data flow between data owner and the cloud. You should be extremely careful when using homomorphic encryption. But here is not the same CCA attack as we mentioned before, because rather than sending the decrypted result to the server, the user should check whether the decryption result is 0. If it is 0, then it will return XI to the server. Otherwise, it will not return anything. So there is only 1 bit information leakage per query. But here we can give a attack that we can reveal 1 bit of user private key by using this 1 bit information leakage. I will give the demo in the next slides. So we can see that to launch a CCA, to launch an attack, data owner do not need to leak all the plain text to the attacker. Any 1 bit information leakage to others will be a security problem. Any 1 bit information leakage will lead to 1 bit key leakage. And the security of homomorphic encryption will drop exponentially. What's more, a 1 bit information leakage is inevitable in real-life application. For example, any action you take will leak some bits of information. An attacker can recover some bits of secret key, so it's very dangerous. Here, there was a simple demo of the attack in FPSI. In this demo, we will show that this CCA attack on this FPSI is practical. Even more, 1 bit information leakage can be used by attacker to recover 1 bit key information. In this picture, I define a function recover key. This function takes some parameter I, where I is the index of the targeting bits of the secret key the attacker wants to recover. In this demo, we first generate a secret key and public key pairs of the BFA algorithm. Then we can call the recover key function with parameter I. Then we can get the S index of the secret key of BFV scheme. The source code is also published in my GitHub. You can check it by yourself. So another attack on this PSI protocol is here. In the PSA protocol, we also need to protect the server's data from the client. This needs the homomorphic encryption have circle privacy. However, most of the homomorphic library have no circle privacy for now. So a malicious client can get extra information of the server's database Y. Here I will not go to detail of this problem because it's not easy to understand. We are writing a paper to talk about this problem, so more detail can be found in the paper. Here is a demo of this attack, but I think it's maybe too complicated to talk it here, and my time is a little limited. So you can find it on my GitHub and read it. So as we mentioned, SEAL does not provide secure privacy on default. The problem has been addressed in SEAL's handbook. To solve this problem, the best practice is to use noise flooding, which means that you can add an encryption of 0 to the result of the computation with enough noise. However, there is no standard interface doing such things. So normal software developer definitely cannot play with this magic, because it's not easy to know how much noise you need to provide. And for now, all practical fully homomorphic library seems to have the same secure privacy problem. There are some ad hoc work around about this, but there was no generic solution to this problem. And the solution, and if you implemented some application on this, you need a crypto expert to implement it. To solve this problem, first you can use an improved version of PSI protocol published in CCS 2018. It is secure against any malicious party. However, it's not a generic solution. As for secure privacy of SEALs and homomorphic encryption, if you want to use it in real application, and you need a crypto expert to review your implementation, and you need professional knowledge on lattice-based crypto, otherwise it's very insecure. SEAL's team is now considering to provide a standard interface to deal with these issues. So another security pitfall of SEAL we found is that the encode of the SEAL will leak some information. Homomorphic encryption is working on some polynomial ring based on some finite field. But the ciphertext we want to process is always maybe some integer, some float, or some string. So we have to convert them to the polynomial ring. SEAL provides an interface to do the converting. You can use integer encoder of SEAL to encode an integer to a polynomial. Then you can work with homomorphic encryption. But the problem here is that the mapping of this encoder is not one-to-one. So there will be some information leakage. This is a demo of the information leakage in SEAL's integer encoder. In this demo, we can see that we have two plain text, M1 and M2. We want to compute M1 plus M2, of course, in the encrypted form. In the first case, we have M1 equal to 2 and M2 equal to 2. So we can easily get that the result is 4. And in the second case, in the bottom ones, we have M1 equal to 1 and M2 equal to 3. So we can easily get that the result is also equal to 4. So attacker should not distinguish those two cases, because the result is equal to the result is equal to 4. So he should not distinguish those two. But here is the problem. Although the decoded version of the result are the same, 4, the encoded form are actually different. In the case, in the upper case, the encoded form is 2 times x. And in the bottom case, the encoded form is x plus 2. It's not equal. So the attacker can distinguish those two, and this is information leakage. So attacker can infer the operator from the encoded form. So the encoder of SEAL is not safe. I have implemented a demo attack on the classical cryptography problem, the median layer problem based on homomorphic encryption. You can find the code in my GitHub also. So this problem might also happen in other homomorphic encryption libs. So be careful when using encoded functionality provided by homomorphic lib. The crypto primitive have a security proof, but the coding scheme might not. As for SEAL, the mitigation is just do not use integer encoder or float encoder. They should consider only demonstrative tools. Instead, you can use a bash encoder or CKKS encoder in SEAL to deal with those problems. There are other security issues in homomorphic encryption. For example, fully homomorphic encryption does not provide security feature such as some commonly known encryption algorithm. For example, it's not an authenticated encryption. You cannot guarantee the integrity of the data. Attacker can use homomorphic nature to modify the ciphertext. So do not use homomorphic encryption for data storage and data transmission directly. You can consider wrapping the FHE traffic inside some TLS or something else. Homomorphic encryption is still a young technology, and there's still a long way to go with homomorphic encryption. Currently, we need a standard documentation for using it, and for making more people to understand it. Microsoft is leading the developing of a standard for homomorphic encryption. Hopefully, it will come in soon. By the way, I think it's important to include some protocol security topic to the standards. And the last thing I want to talk about is that fully homomorphic encryption cannot actually compute any arbitrary program. Because arbitrary function in fully homomorphic encryption, that means that you can do arbitrary addition and multiplication. But arbitrary addition and multiplication does not mean that you can run arbitrary program. For example, you cannot do a comparison directly. So the if range is not supported here. So fully homomorphic encryption actually cannot do anything you want. I think the famous metaphor I mentioned before should be updated like this. The worker in the picture should wear some ice shard, and so she cannot see the jury. All the box in the right picture should be an OP code 1. Just like you cannot do some comparison in the fully homomorphic encryption. Okay, so here is the conclusion of my talk. In this talk, you can see that fully homomorphic encryption is useful in many scenarios, and its performance is actually improving and accessible for now. But homomorphic encryption cannot solve everything you want. It cannot really run arbitrary program, and there are a lot of security pitfalls and security risks to using it. It still needs a long way to go to be widely used. And it's extremely dangerous to use homomorphic encryption without an expert for now. The crypto community needs to focus on building some secure protocol on homomorphic encryption. And at last, I want to thank K9 of Microsoft Research and Chen Hong of Alibaba Zhiniang Lab for the valuable comments and suggestions to these talks. And that's all for today. Thank you for your time.